Okay, do a little review today on equilibrium. That is, making sure I finished. Did I finish?
You did.
Let's see.
I think you did.
You were in person, and you were on Zoom.
Yeah, I think you got through all your slides.
That looks familiar. Yeah. Okay.
You said that video is still up there?
Should be. Yeah, I don't take them down.
Where do you post those? Where is it? I haven't looked for one yet.
I put them under the folder for each exam. So this will be exam 3.
So it's under the exam folder.
Well, last one was exam 2, so it'll be under exam 2 folder.
Okay, under each chapter.
Oh, that's right. In this one, I have them under chapters.
Okay. Yeah, last chapter I got on Khan Academy and watched a few of their videos to help me too. I mean, it helped a little bit. Just another explanation of it.
Oh, yeah.
Other problems being looked at. Pretty handy.
Okay. Topics that are vexing you at the moment.
Just all of it vexes me, really, honestly.
Well, we'll start with the basics then. How about number 1? If we have an equation like this, okay, we've got 2 gases and 1 solid. So we've got to find out which one of these statements is false. First one, if the system is heated, the right side is favored.
I'd say that's true, right? Because if you, or no.
Okay. We're not told whether this reaction is exothermic or endothermic, so we can't use that approach. We have to use an alternate approach. Let's write the expression for K here, first off. Remember, solids don't count. Pure solids, pure liquids don't count. You have to use only.
Ooh, can we move that computer? Because you're right in my line of
All right, let me see.
vision. Leave the end.
Okay.
That'll work, thanks.
So we have hydrogen iodide to the 2nd power divided by hydrogen to the 1st power, and solids left out.
I'm going to assume that will be the reason you need the solid out in the chapter.
I'm sorry?
The reason you need the solid out is to explain the chapter.
Yeah, I was explaining class too. To make a long story short, pure liquids and pure solids in an equilibrium situation, their concentration does not change. Right? That's, for all intents and purposes, it's 100%. Right? Same for liquids. But gases, their amounts do change in a reaction, so their concentrations change. And aqueous solutions, or any type of solution, their concentrations will change. But if you want to think of it this way, the effect of this one is buried in that term. Okay, so let's see, we need to figure out how do we approach A. All right, we've got our equilibrium expression. We have to, well, the approach that I took in that answer was that as we increase the temperature or add heat, we're increasing collisions between this one and that one. So the reaction rate should increase. The effect should drive the reaction to the right. Now, if you have access to the thermochemistry, is it endothermic or exothermic, then you can make a statement concerning if this were endothermic, the heat would be a reactant. And if it were exothermic, heat would be a product. And in that way, you can say if it's exothermic and we add heat, then it's going to drive it back this way. If it's endothermic and we add heat, it'll drive it that way. But in the absence of that information, we have to sort of make some assumptions, and that's where we end. This is a heterogeneous equilibrium.
Gas solids.
Right. You've got, even though the solid is not part of the equilibrium expression, the balanced equation does include different phases. So different phases means heterogeneous equilibrium. For C, if the pressure on the system is increased by changing the volume, the left side is favored. Okay. Let me read that again. If pressure on the system is increased by changing the volume. So we increase the pressure, we're squeezing this down. So how is the system going to respond? Well, Chatelier says it'll respond to reduce the effect of the disturbance. So if we squeeze it down, we're trying to squeeze 2 moles into a smaller volume. And its response is to make fewer gas molecules.
That's what that says.
Yeah. Yes. So if we squeeze it down, it's going to drive the reaction back this way. Because you've got 1 mole of gas here and 2 mole there.
That doesn't sound like the case.
Okay, you have a counter argument?
I don't know. I guess I just kind of assumed that it would more pressure would just kind of increase the rate of reaction, turning it into the QHI, because it causes more collisions between the H2 and the I2.
Okay, that's one logical approach. The problem with logic is it doesn't always work.
Especially with that chapter.
So, well, no, logic is okay as long as it agrees with reality. And the reality is when you compress this system, it does go back that way.
Does that happen with all heterogeneous reactions?
No, just with gases.
Just with gases.
Right. If you compress this system, it's going to drive the reaction this way because you've got 2 moles of gas here and only 1 there. So it's going to relieve the increase in pressure by decreasing the number of moles.
Which will kind of decrease the number of individual like particles bouncing around.
Yeah.
Right, some of it's gonna go back to solid. Is that the case?
Yes, it'll produce, right. It'll produce more of this. It'll produce more of this because,
I guess that's why. So the solid's gonna condense back, and then that space then's only gonna be taken up by the hydrogen with a smaller space available.
yeah, in this type of discussion, you really assume that there's no essential volume change due to the solid.
Well, I guess that's what I mean is like that, because it's gonna just like not take up the space. And so if I'm
Oh, I see. Yes.
If the volume and pressure, if the pressure's going up and the volume is getting smaller, that iodine is just going to go back to being not taking up space by
Right.
becoming that solid particle.
That's true.
So that the hydrogen has room to freely move about.
Yep.
That's kind of how my brain thinks about it.
Right. We're taking part of that volume and storing it in this.
Right.
That's true. Okay, and D, adding more hydrogen increases the equilibrium constant. If we add more hydrogen, what does it do to this value? Equilibrium constant is constant. It doesn't change at all, no. It will temporarily increase this value, but then it's not at equilibrium.
So it will eventually.
Once it reaches equilibrium, that K is still the same. Right. Now, if you change the value here, you will change the value of Q.
What does Q stand for?
It's a non-equilibrium expression that's analogous to the equilibrium. In other words, you set it up the same way, but the conditions are not equilibrium. We use it at the start of a reaction to determine which way the reaction is going to go. It's going to go to the right, it's going to go to the left. If Q is larger than K, that means this is favored. This is larger than that. So that means, right, if Q is larger than K, it's going to go back this way because you've increased that amount. But if Q is less than K, that means you have more of this, and it's going to go to the right. That's important to know when you try to do equilibrium calculations. Let's see, what did we say? D was,
False.
yeah, D was false. So we found the false one because K doesn't change. Now, the equilibrium constant doesn't change. The equilibrium position is different. The equilibrium position refers to the actual concentrations of the reactants and products. So if you add some of this, it's going to shift that way, but it's not going to use up everything that you put in there because it's aiming for that equilibrium position. Equilibrium constant. So the position itself will have more hydrogen in it, but it'll also have more hydrogen iodide.
There's more reactive product.
Yes. But it won't use all of it up that you added, the extra. So that's a distinction between equilibrium constant and equilibrium position. Okay. Was there an E? Might as well do E. Oh, 2 of these. No, I'm still 1, excuse me. Removing HI as it forms forces the equilibrium to the right. Okay. That's foundational to equilibrium. You remove part of this, then it's going to keep shifting that direction until it reaches equilibrium again. Okay. Number two, we're trying to find out which one's true instead of false. So we're just saying an equilibrium system will take a short time to reach equilibrium. The following is true for a system whose equilibrium constant is relatively small. Okay. So if the equilibrium constant is small, and we mean much, much less than 1, what does that say about the equilibrium? Well, if we have something like this, this is my generic equilibrium situation. And we say K is that. Then what that means is that this is very small compared to that. So we can say this is large, that's small, which means the equilibrium favors reactants. They're large and not products. So the equilibrium position is going to be on this side. Okay, that's our starting point. That's what that means. It will take a short time to reach equilibrium. Does equilibrium have anything to do with reaction rates? Sort of, but but once you reach equilibrium, it doesn't matter what the rate is. And it doesn't say anything about how fast it gets there. Some equilibria are established like that, and some take a long time. Like the equilibrium position for a diamond decomposing to carbon is like in the billions of years. But it will happen eventually. It will take a long time to reach equilibrium. Well, same argument. A and B are both false. How about C? The equilibrium lies to the left. Yes, we just established that. With a small k, the equilibrium means that this is small, that's large. So that means it's over here. So this is true. We found our true statement, except that we also have 2 of these. So we better do the D also. The equilibrium lies to the right, no. So that means E is false also, because it says 2 of them are true. So C is the only one that's true out of those statements.
What if the equilibrium constant is large?
If it's the other way around, that means that this value is very large compared to that value, which means the equilibrium lies over here for the products. Now your book and the authors will say, if K is equal to 1, then that's equal to that. Well, yeah, the entire expression here is equal to that expression. Right? But concentrations may not be exactly equal. Why? Because you've got these powers.
So even on 4 times 5 over 10 times 2.
Yeah, if you've got powers in there, then you can't say that these concentrations are equal to those concentrations. But the expression of this is equal to the expression of that. That's true. For K equals 1.
K does equal 1, like, then
You need an example, don't you?
well, I mean, which side is it really favoring? It's not. It's just like what? I guess what can we say about that? What
Okay.
can we say if then?
It doesn't favor one side or the other. Not significantly.
Okay. I'm okay with that. Just
Okay. Okay. Let's see.
Sorry. So great.
All right, let's just do 3 then. As long as we got a different topic each time we move to a new question, then yeah, I think it's valid. If we get a repeat, then we'll skip that one. So for this equation, carbon dioxide gas, hydrogen gas, and carbon monoxide gas.
Are all of these states of equilibrium studied in just laboratory conditions? And then, like, I guess I'm always wondering about real world application and seeing it, you know, in nature.
Yeah, they're usually
I mean, obviously, we study these things in
Yeah.
one context to understand them in a greater context. So that's
Yes.
where my mind wants to go. Give me the greater context.
Yeah, that-
please.
Okay. Sometimes the laboratory studies are induced by real world problems. Right? But eventually you've got to work out the details, the chemistry in the lab. Then you can scale it up to real world applications, either chemical engineering or even environmental. So what's happening here? Well, carbon dioxide is combined with hydrogen to make carbon monoxide and water. I can't give you a real world for that one, because it's difficult to find pure hydrogen in nature to conduct that reaction. Now, since this is equilibrium, it could go backwards. Now, that's a possibility. Carbon monoxide and water could make CO2 and hydrogen. Now, I could envision a hydrogen energy economy where you have carbon monoxide as a product of some other reaction, combine it with water and make hydrogen, make some useful product out of it. And then you could run that, either burn it, or you could run it through a fuel cell, make electricity.
Isn't hydrogen very abundant?
Hydrogen abundant? No. Not on Earth. It is in the universe. Yeah, it's the most common element in the universe. Right?
That's what I thought of.
Oh yeah, it is. All stars. Right. They're mostly hydrogen. Right, we can't access that source. And there's some planets that have a large portion of their atmospheres hydrogen gas. Now, Venus is carbon dioxide and sulfuric acid. I guess the closest would be Jupiter. Yeah. But it's got a lot of other things in there too. That gives it pretty colors. Okay, so we're also given the delta H for this reaction. So it's a plus 42 kilojoules. Remember what that means? Endothermic, yes. So that means this is as if you put the heat in on that side.
And then on the other side, that's less.
Well, if you consider it a reactant, the heat is stored in these products. Right? It just goes in here and disappears. If we say that K equals 1.6, and that's also equal to, these are all gases. Yes, all gases. Okay. And this is at 1260 K. So this reaction takes place at very high temperature. If 0.15 mole each, I'm just putting information up here so we can get a full picture of the reaction conditions. And these are all in 1 liter. These are starting conditions. So that's per liter, which means what?
Yes.
That means it's 0.15 molar for each one. That's your starting condition. Now, as it turns out, for the question that's asked, that information doesn't matter. Okay? So the question has to do with temperature. So for A, the temperature would decrease and the mass of CO2 would increase. So what do we need to do? We need to find out what the Q is, right? Because this is a starting position, so we have to compare the Q to the K to know which direction it's going to go. Because we're not adding any heat to it, so we can't talk about it in terms of Le Chatelier. We're adding or subtracting heat. So we have to talk about it in terms of Q. So what would the Q be? Well, it'd just be each one of these times. So it's 0.15 molar squared over 0.15 molar.
Dr. Bly?
Yeah.
I have a question.
Okay.
Could we not, is it not logical or right to just make the conclusion or like, I didn't read the answer, I just read the question, and my logic said, well, if this is an endothermic reaction, then if we're adding heat is a reactant, then why wouldn't the temperature decrease as we made something else? Like,
Oh, we're not adding heat.
we're not?
It's at 1260 K, and it's an insulated vessel, so we're not adding any heat to it.
Okay, so it already had the heat.
Yeah, the heat's already there.
So, okay, so, but my brain was still like, well, it's already still there, but for the reaction to happen, something's actually happening, and it says, then as the system came to equilibrium, so something is happening. And I'm
Oh, yeah.
like, well, then for that to actually happen, then the heat has to come down, and the CO2 has to come down to make the product. So
If it moves that direction. But with these concentrations, which way is it going to go? Is it going to go that way or this way?
So my question is it wrong for me to logically think in that way, or should I really think about like doing that math to get the
Yeah.
answer?
Yeah, you have
That's
to do
my
the math to know which direction it's going. Yeah. So this is going to be 1.
So I just got lucky in getting the answer right. That's the case.
I guess.
Because I didn't do any math. I just read it, and that's what my brain made sense of it as.
So if Q now we know is less than K.
Is that always the case?
No.
Just this?
No, it depends on the concentrations. These are starting concentrations. So we're not at equilibrium yet, right? It's going to go to equilibrium unless, if this were 1.6, we'd already be at equilibrium, right? But we're not.
Okay.
So if Q is less than K, that means that this is smaller than it should be, and this is larger than it should be. So if this is smaller than it should be, then it should go that direction, to the right. The reaction is going to go to the right, is it not?
So CO2 decreases.
Okay, right. So since it's going to go to the products, it's going to consume some heat, right? So temperature would decrease as we consume that heat, and then we're going to produce products and consume reactants. So it'll either be A or B, and then we got to see what else. And the mass of CO2 would increase or decrease? Decrease. This is going to decrease. Temperature is going to decrease. So B has to be the answer. Yeah, whenever you get a non-equilibrium situation, you've got to determine which direction the reaction is going to go. If you were told that this was equilibrium, then any change you make to it, you can logically deduce which way the reaction is going.
Can you back up several sentences and just repeat? Why is it by knowing that Q is less than K, why is it that we should understand that the reaction will be going to the right?
Okay. At equilibrium, these concentrations are balanced, so to speak. And they're balanced at that value. Okay. So if we see that Q is less than K, then which way is the balance shifted? It's shifted towards smaller amounts of that and larger amounts of that. That makes the Q smaller. If we start from this position, they would say, reduce this and increase that, then you get a smaller value. Right? So that's Q is less than K. Well, if this is smaller than it should be and this is larger than it should be, it's going to shift toward these right here to reestablish the 1.6. So if it shifts toward these, that means products. So if Q is less than K, we're going to shift toward products. Do I need to say it a different way?
I don't know. Then I guess I understand what you're saying. I guess it was the connection of coming to that conclusion for me. And I mean, I got there my own way, but still it didn't exactly match up with how you determined that answer.
Oh, stepwise, you've got to decide which way is the reaction going. And if Q is less than K, it's going to products based on that explanation. Okay, now we know it's going to products. What is happening? Well, as far as the physical reactants and products go, we're going to consume CO2 to that side. So CO2 is going to decrease. But if it's endothermic, heat is also a reactant, and we're going to consume heat as well.
Okay.
So the temperature has to decrease.
I just made the connection between everything, why you did the Q thing. I
Okay.
got it now.
Okay.
I mean, it's like having the dominoes all lined up, but I'm only knocking over a few. Whereas you've got the whole line, and I'm like trying to figure out which ones I'm missing.
Somebody stole some Dominos, so it won't go all the way.
Yeah.
Yeah. Okay. All right. Let's see here. That was 3. Wow, we're off the first page.
Sorry,
That's-
I don't mean to be painful.
No, that's what we're here for.
We're making leaps and bounds at 9%.
Let's see. Let's look at, I think. Now, number 8 is a Le Chatelier's question, but it's in terms of colors. And it might be well to look at it that way because we've been theoretical so far, just saying concentration this and concentration that, but color is something you can wrap your eyeballs around.
Literally.
Yeah. So if we have this complex ion, and then we add some chloride ions to it, we get this complex ion. And then our next to the last exercise is going to be complex ions. That's another reason I want to look at this one. So this is going to be a pinkish color, and this is going to be blue. Okay. Now, we're saying that we are at equilibrium at this point. And the equilibrium, when we add cobalt-2 chloride to water, it forms this hydrated form. So cobalt-2 combines with water to form a complex ion. It's still in solution, but it changes color. It becomes pink.
Chloride, cobalt chloride breaks up as an ion.
Right. So you've got the chloride over here, and you've got the cobalt over here.
Might be wrong in saying this is a non-two-step reaction, like one of the steps in the reaction.
Not necessarily. It can be a standalone. Yeah. So let's see. Do the charges balance? Well, if we have a 2 plus here and a 4 minus there, it means we got 2 minus extras. And then we got 2 minus extras on that side. So the charges balance. That's important. And the number of waters is the same. The number of chlorides is the same. Cobalt's the same. So the equation's balanced. And it sets up its own equilibrium. All you have to do is just put it in water. And that's your equilibrium is established with pink as the dominant color. So now, what if hydrochloric acid is added? So we're going to add hydrochloric acid. Okay, we're going to add chloride ions, is actually what we're doing. So if we add chloride ions, what are we going to do? Well, if it's at equilibrium and we add chloride ions, the chloride is going to combine with the cobalt and make this, the blue. Right, so at some point, it should become more blue. It may not be. It all depends on how how much of this you add. The more you add, the bluer it gets, right? At some point, it's all blue and there's no tinge of pink left to modify the color. Okay. That's why we say more blue and not just blue.
So basically, when you add cobalt chloride in water, it turns pink.
If you add,
Hydrochloric acid.
right, if you add hydrochloric acid or any chloride actually, as long as it's not more cobalt chloride. There's some other chloride in it. You could probably do the same thing with sodium chloride. As long as you add the chloride ion. We'll drive the reaction that way. So A is true. It would not become more pink because pink color refers to a reactant. You're driving it toward products.
So if you add cobalt, it turns pink.
Yes. Yes. So let's see. A is true. B is false. The equilibrium will shift to the right. Yes, we just said that. It'll become more blue.
Well, that's interesting. So when you say cobalt, you think of the color blue, but it's actually pink too.
Well, yeah. I mean, there's more to it than just the element. And then D is false because it's the opposite of C. And then E is true because A and C are true. Then two of these is true, and E is the answer. Take a second to sink in.
So the equilibrium will shift to the right because
Simply because you added reactant.
so it'll react faster.
No, speed has nothing to do with it. Well, as a practical matter, yeah, it happened pretty quick, but that has nothing to do with the equilibrium
Because
position.
how do we know that that's what happens if we without knowing concentrations? Like, how do you?
Oh, because your starting position is equilibrium.
So you would do K is equal to CO and over top of the other side, and because you added more to the bottom, it would make the constant smaller, which would make it shift the other way.
If you increase the denominator, it's going to shift. Some of that is going to be consumed and transferred to the numerator to reestablish equilibrium. Yeah.
Because K is constant. So I guess what really changes Q.
Yeah, right. If you add some of this, well, since we're already at equilibrium, we don't need to know Q. We're adding some of this, then Le Chatelier takes over and says it's going that way.
So I guess just thinking about the question from where you said the starting point was I guess the point where it didn't really sink in. Like, know where you're starting from. What's your
Right.
starting point?
If you're already at equilibrium, then you can use Le Chatelier. If you're at a starting point and that you're not told that it's equilibrium, then you have to
No Q.
calculate Q and compare it to the K. Yeah. Unless, another possibility is, if you're given reactants and there are no products, it's automatically going that way, right? If these are both zero, it's got to go that way. Or if you're adding these, it has to go this way. Okay. Let's see. That's another shift problem. We need to do some with math involved. 21. 21, we start to get into equilibrium calculation. Okay.
Visible.
Yeah.
That's visible.
Okay, we got at 500 K, 1 mole of gaseous ONCl is placed in a 1 liter container. At equilibrium, it's 5.3% dissociated according to the equation. So this is our balanced equation. And it's a simple dissociation to these products. Our starting position, 1 mole, I guess they're all gaseous. That has to be. Nitric oxide, chlorine gas, they're all gaseous. So 1 mole in a 1 liter container is 1 molar concentration. Okay. At equilibrium, this is 5.3% dissociated. 5.3%. We're actually losing 5.3% of this at equilibrium. Okay, that's what that means. If it's 5.3 dissociated, that's how much of this is converted to that. Okay? So now let's set up our ICE table. That's probably new to you. ICE means initial, change, equilibrium. So your initial state, in this case, is 1 molar. Let's see, separate that from this. And I set it up underneath the balanced equation so I don't have to rewrite all that stuff in another table. And you got 0 of those. Right? So we know which way it's going. Right. Now let's see if I've chosen, I was looking at my problem here to see if I've chosen the correct values for okay. I'm gonna change it a little bit from here. Let's say instead, since this is 2 and that's 2 and that's 1, let's make this one X. So we're going to add some X here as this dissociates. But for every one of these X's, we have 2 of these, right? And for every 2 of those, we have to lose 2 of these. Okay? Right, I'm not following this one exactly.
So for every Cl2 we gain, we're going to lose 2.
2 of these, right? Because of 2, 2, and 1. Stoichiometry. So we're going to lose 2 of those, and we're going to gain 2 of these. For every one of those, we get 2 of these, and we lose 2 of those. Okay, so the equilibrium situation is 1 minus 2x here, and 2x here, and x there.
Why can't you do, well, if initial is 1 molar and we know that at equilibrium we've lost 5.3%, can you not just say 1 minus 5.3% for equilibrium under that? Does that not work?
Yeah,
So you,
yeah, 2x, right.
so could it be 0.947 in that column for equilibrium?
Yes. Yes. if 2x is equal to 5.3% of 1, that would be 0.053, right? Of 1.
Which is 0.947.
So that's our equilibrium position for ONCl. And then this is going to be 0.053, and this is going to be half of that, 0.0265. Okay. So now that we know what our values are at equilibrium, we can calculate the constant. Okay, so K is equal to NO squared Cl2 divided by ONCl.
So the ice chart, you add initial change. So
Right.
like you just go down the vertical column. So
Yeah. Right.
just a little review.
So NO then is going to be 0.053 squared and 0.0265 divided by 0.947 squared. Now, I'll see if I get the same value as here. 0.053 squared and 0.0265, 0.947 squared. So I get 8.3 times 10 to the minus fifth. Yeah, close enough. 10 to the minus 5. That says 8.5. Actually, I like this way better than the way I have it in here. Which means if you look at the answers, the best answer is going to be whatever is 10 to the minus fifth. That's why A would be the best answer, if I did my calculations correctly. Yeah, should be.
Oh, you did it totally different.
Yeah, it is a lot different in the work problems than I did it here. But I do like that one better. I think what I'll do is photograph this one.
I think it's because here at the bottom you have 0.027 instead of 0.0265.
That explains it.
Because you do end up with, well, you get the right answer anyway.
So I'll modify this one for the next class.
Not working with the fraction is nice.
Huh?
So not working with the fraction is nice.
Yes. Okay. So that's actually calculating a K value from this dissociation information.
Oh, that's okay. I got it.
Let's see. 22, we really don't even need, let's see, KP. Number of moles. CO2. Yeah, for 22, you don't even need to know KP. Oh, yes, you do. Because the KP gives you the pressure at equilibrium. But you're going to use the ideal gas equation. Did that give anybody fits? In other words, do we need to do that one?
Do you believe it might be your test?
Oh, I don't know. I made the test up a long time ago. Let's say 22.
I'm going to assume KP is the constant pressure, or is P the name of the system?
I'll explain in just a second. CO2. Okay. Equilibrium expressions are basically all the same. Products over reactants. It just depends on what version that you're using. If we use molarity, then we usually say either just plain K or KEQ. If we're using partial pressures for gases, then we use KP. If we're using, say we're dissociating water, say an acid solution, then we'll use K to the A, which we'll do not this week, but the 2 weeks when we do acid-base equilibrium. And there are a whole host of them. Just depends on the type of information that you're using to build them. And the Ks are never quoted with units. The reason being that with those powers in a balanced equation, when you plug those powers in, sky's the limit on units. It just becomes too unwieldy to report units for every K value. So you just have to know what's the origin of the K and then use it properly, and your answers will be all right.
So there are many different K constants.
Yes.
Types of constants.
Right. If you look up Ks in a reference manual, they'll never have values. They will tell you where the K came from. You have to know that. Okay, so for this reaction, Kp equals 1.16 at 800 degrees C. And Kp is going to simply be the concentration. Well, actually, that's not right. That's concentration in terms of molarity. It will be partial pressure of CO2. Okay?
CO2 is the only thing that will be giving off pressure in that, right?
Right, because these are solids. That's the only term that matters.
And there's no vapor pressure equivalent for solid, I'm assuming.
Right. Okay, so if other starting conditions, 31.3 gram sample of calcium carbonate is put in a 10-liter container. So volume equals 10 liters and heated to 800 degrees. what percent of calcium carbonate will react. So percent reaction, that's what we're looking for. Okay. So this is going to be, and the partial pressure is, you have to assume that the partial pressure is atmospheres. So at equilibrium, in that enclosed vessel, the partial pressure of CO2 is going to be 1.6 atmospheres. That's equal to your pressure value. Okay, if we solve this for, what we need to know is how many moles of carbon dioxide are produced. We know the pressure at equilibrium, right? This is an enclosed vessel. So when we heat it to 800 degrees, it's going to produce a partial pressure of 1.6 atmospheres. Wait a minute, did I? Oh, I'm sorry. 1.16. Thank you. So it's going to produce a partial pressure of 1.16 atmospheres in that enclosed vessel. So we know, well, we're going to solve for moles, actually. That's what we need to know. How many moles of CO2 are produced? Because that's the only way we can get back to how much of this was consumed to answer that question. So our partial pressure is going to be 1.16 atmosphere. And then the volume is 10 liters. Okay. And R is 0.08206 liter atmospheres per mole K. And then, right, and then temperature is 800. Well, I said C. Is it C or K?
It says 800 degrees Celsius.
Celsius. So we need to add 273, which will be 1073 K. So this is 1073 K. Say again?
So I'm really glad you don't push the 0.15 at the end of that Kelvin.
No. That'd be overkill. So I get 0.1317 moles of CO2. Now that we know how many moles of this are produced, and we know the stoichiometry, like one of these for each one of those, then we also know that this is that many moles of calcium carbonate were consumed to produce that much CO2.
Is it just 1 to 1?
Yes, just 1 to 1.
Yeah, I know.
Yep. Question?
Okay, I was just doing my math, so 0.1317. So
Is that what you got?
yeah, so that was solving for the number of moles for
Carbon
CO2.
dioxide. Right.
And now you're looking at the coefficients, and that's why you said it was 1 to 1.
Right. I just didn't put the conversion factor in there because they're 1 to 1.
Now we need to see how many moles 31.3 grams is of CO2.
How many grams of this were consumed? Right. So what we need is the molar mass of calcium carbonate. So I don't have to look calculated. 100.1. Right.
40 plus 12 plus 48.
So that gives us how many grams of calcium carbonate were consumed in the process. And I get 13.18 grams. And then the question is, okay, so I'm doing it a little different than this one. Let me be sure I'm not. Yeah, what percent was reacted? This should work. So in the way I worked it out here, I converted this to moles and then compared it to this moles. Let's see if it works out the same. So if we have this many moles consumed, the percent calcium carbonate consumed equals 13.18 of 31.3.
Well, can you just say what percentage is of 31.3 is 13.18?
Yeah.
Yeah, that's what I'm asking.
13.18, 31.3. So I get 42.1%. Yeah. Does that come out the same? Close. Yeah. So if we use best answer, would be B. I'm gonna take a photo of this one too because I worked it differently this time. Okay. So let's see what other mess we can get into here. How about number 26? This gives you some practice calculating combined equilibrium constants. In case you have to combine two or more equations to get the one you want, what do you do with the K's? So if we have, let's see, 26. If we have these two equations, and there's a K associated with that one, and then we have this one, and a K associated with that. And the resultant equation is going to be what's the K? Yes, in terms of these. Because we're going to add these two together in some form or fashion to end up with this one. So let's see. This one's okay because copper's on the right side. It's just not the right amount. Okay. How about this one? CuO. This one has to be inverted, has to be flipped to give you that one. So this would be,
Well, I don't follow you there. What do you mean?
well, if you're going to add them together, you got to put this one on that side, on this side. If you don't put it on that side, you can't add them together. Because when you add them together, you're going to end up with this over here instead of over there. So we have to flip this one. We have to invert it. Okay, so what does that do to this one?
It's 1 over 2.
Yes.
I'm still kind of lost on that. Like, you didn't say things differently enough for another domino.
Okay, do you remember Hess's law? Where we add equations to get the enthalpy of the resultant equation? How you add those together? You don't remember that?
Not so much.
I remember that. I just didn't know that we would have to do it for this one. I didn't know that these equations were being added together.
Yeah, you can add them together. Yeah, there's no law against that. So this one is okay now because we've got two CuOs there. So I'm going to use this one. Then what do we need to do to this one? Well, it's okay as written, except we need half of it. All right. So half of that equation would be okay. What does that do to this one? There it is.
Well, it just works out really well.
If you divide through by 2, or you take a half of this one, then that changes this K to a half. Okay, so let's see if that gives us what we want. On this side, we have 2 Cus. We have a half an oxygen here and a half an oxygen there. Okay, so those are good. This is a Cu2O, and this is a Cu2O. So those cancel. And that leaves us with nothing on that side and this one on that side. So we've got all the terms that we need out of those two equations. And then what happens to, let's see, we're going to use this one and this one. So what happens to the K value when you add equations together? You multiply the K's together. So K1 to the half times K2 to the minus 1. Right. So at this point, you look at your possible answers. And since this is to the minus 1, a valid expression of that one would be, put it on the bottom. And that's what you would look for here. Or you would try it that way and say, it's not there. So let's change it a little bit and see if it's there now. Yeah, there it's now, E.
So, did you really have to work out all of the equation stuff the way that you did to get there?
Yes. I don't know any other way.
I mean, the first step we did was say, well, we've got to invert that one, and then you inverted it, and then.
Right.
And
And then we had to use this one, but this one has too many coppers. You only need half as many. So we had to take half of that equation. And half of that equation changes the K to 1/2 power. Didn't I explain that in the PowerPoints? What happens to the K when you modify equations like that?
I mean, you could have. It doesn't. It's
Okay.
maybe it's not that stuck on me.
Let's try a simple one. Well, okay, we'll do it this way. Okay, so the K for this one is going to be okay. Now what happens to K if we take half of this one? Okay, so that would be A divided by 2, right?
So it's changing the answer.
And B divided by 2, C divided by 2, and D divided by 2, right? That would change the coefficients, right? So the coefficients now would be so if we gather all of those half powers, we have right, if you take that half and go through here, it's half of this one, half of that one, half of that one, half of that one. So that's why this value is the same as that one to the half power. Or if you say double it instead, then it would be a 2 out here instead of a half. Okay? Now what happens if we invert? All right, so let's say let's do this like that. All right, so what happens if we invert that equation? Then we have this one. And the K for that one is okay, what relation is this one to that one? It's just the inverse, isn't it? All right. So this one is the same as, let's see, then this one would be that one, like that, or K to the minus 1 power. That's why it works. You might need a break.
Yes.
Okay.
That shows the lead there.
Yeah.
I need help with, when I'm writing lab reports, I never know like what to put in the conclusion, like section. I don't really know I don't know what to say.
Okay.
Like what helps wrap up a report like that? Like, I just feel like am I just regurgitating, reiterating, like what happened in I just need a little guidance.
That's part of it. That's part of it. That's a good way to start conclusion, is summarize what you did.
Right.
And the results. But the conclusion it involves some thinking, what does this mean? And that's why I gave you guys that other report.
Which other report?
Well, it was a sample report.
I don't know if I have that with me. When did we get that? Is that at the beginning of the
Oh yeah,
term?
it was the first day.
Let me see.
So, and it's on Blackboard.
It's on Black.
Yeah, oh yeah.
I don't know, that's just the part of the project I always am like struggling to figure out what is it I'm really trying to say here.
And your, this is what we're looking for. Did they support your hypothesis? Well, sometimes you have a hypothesis, sometimes you don't. But did the results support what you thought you should get? In other words, if you don't have a hypothesis, that's what you think. And can this be applied to some real life situation? So this conclusion is a summary. And then part of that fits into this one and that one, sort of overlap.
Are you looking for a section that says analysis? Like,
No.
okay.
No, analysis is just a way for me to determine if you've synthesized what you've learned in the experiment.
I'm trying.
Let me pause this so we don't. Okay, we're going to look at number 36. So at a certain temperature, this reaction has a K value of like 7.5. So if we place 2 moles of NO2 in a 2-liter container, 2 moles in a 2-liter container is 1 concentration. 1 molar, right? And that starting position is 0. Calculate the concentration of N2O4 at equilibrium. All right, so actually, this is initial. Then we're going to have a change, and then we're going to have an equilibrium situation. Right. So the change is going to be, be sure I'm looking at the right one again, 36. Yes. So the change is we're going to produce some of this, which means we're going to lose twice as much of that because of the stoichiometry. Okay? So this is going to be 1 minus 2x, and this is going to be x. All right, so this K is equal to N2O4 divided by NO2 squared. That means N2O4 is X. And then NO2 is 1 minus 2X squared. Okay, now all we have to do is solve for X. And since we've chosen X the way we have, then all we have to do is find out what X is, and that answers the question.
Would it always be 1.0 or is
No, it's 1.0 because we've got 2 moles of that stuff in a 2-liter container. That makes it 1 molar, right?
So the initial is always going to be in terms of molarity.
Well, in this case it is. It could be partial pressure. If it's given as partial pressure. But in this case, it's molarity. Okay? So there are 2 ways to work this. You can square this and then solve for X. Actually, set it equal to 0 and then solve your quadratic for X. Okay. That would be the surefire way to get there. The other way is to assume that X is very small, and that removes that X squared term, and then solve for this X. But then you have to do the 5% rule. That is, plug that X back in here and see, is it within 5% of that value? If it's not, then you got to go either go back and use a quadratic, or you can iterate. Plug the value in here, solve for that one,
So
and then try it again.
what would happen if you were to say, just try and foil that 1.0 minus 2x? You know, 1.0 minus 2x, 1.0 minus 2x, and then 1.0 times 1.0, 2x times 2x, 1.0 times 2x, and then 2x times 1.0.
Oh, you have to expand the polynomial. Yeah. That's the only way to solve it, as a quadratic. Right, you have to expand this. So that would put X goes on top, and then on the bottom is 1.0 times 1.0, and then 2x times 2x is 4x squared, which is a plus because it's minus here. And then 1 times this is minus 2x, plus minus 2x is minus 4x.
That's how you get your ABC.
Yeah, we're getting there. But since we have X up here, we still have to solve for it. So what we have to do is take this one over on this side, multiply 7.5 times that. 7.5 minus, okay. Oh, 1530. Right, 4 times 7.5. 2 times 7.5 is 15, right? And 2 times that is 30. So that's this one times that. And then this one times that is plus 30x squared equals x. Correct?
X over 1. All right, 7.5.
Right. And in order to solve a quadratic, one side has to be equal to 0.
So minus x.
So minus x on this side would be 7.5 minus 31x plus 30x squared equals 0. And then we solve the quadratic. Okay, so
If you have some glimmer of memory, you're way ahead of where I was last week.
so if we say, where's my calculator? This is what x is going to be equal to. I'll just put this up here. This is, actually, we got it reversed. This is the A term, this is the B term, this is the C term. So minus b plus or minus the square root of b squared minus 4ac all over 2a. So our b term here is minus 31. So it's a minus 31 plus or minus square root of minus 31 squared minus 4 times a, which is 30, times c, which is 7.5, and then all over 2 times a, 30.
It's the value of a, not the x squared. I'm assuming.
Say again?
The value of the coefficient of a, or the,
Yeah, oh yeah, the coefficient, I mean,
we're not worried about x squared.
no. It's just the thing that makes that a is its position in front of x squared. Right.
So a is always x squared, b is always x.
Right.
C is always,
Yeah, it would be better if I had flipped those around. So it'd be x squared x and constant. But then x can either be, I don't want to have to do all that again, so we resolve these two terms and we get 0.647 or 0.386. So then you have to look and see which one makes sense. If 0.647 were x, then what's 2 times 0.647?
1.2.
Right. It's more negative than this, so that gives you a negative number here that can't be.
Possible.
Right, it's impossible. So it has to be 0.386. And that's the concentration for that.
Right. It's 0.386.
Yes.
Or partial pressures if it were in that kind of situation or whatever it is.
Oh.
Yes.
Yeah, if it were partial pressure, they'd have to give you the pressures and not the concentration.
Did you use the quadratic formula to solve that? If it were a similar setup.
Oh, partial pressure? Oh, yeah.
So
Yeah.
it'll work for anything that has squared x.
Mm-hmm. Right, doesn't matter. You want to work it out as an iteration? So if we were to take this right here and say, let x go to 0. Say x is small. Just assume that x is small. So that would mean 7.5 equals x over 1.0 squared. Right? So that would be x equals 7.5. We know that's not right. Right? Because if it was 7.5, it'd be crazy. So what you do is you take the x and this x and you put it back in here. So this is our next iterations. I hope this works. 7.5 equals x over 1 minus 2 times 7.5.
But not the x on top.
Right, because that's the one we're going to solve for. You know, this isn't going to work because that makes x even larger. It's going the wrong direction. So let me see, what have I done wrong? If we're going to iterate, okay. You can't do it that way and iterate with this one. What you have to do is pick something that's closer to reality. We know that x can't be any larger than 0.5, right? Because if it's larger than 0.5, then this goes to 0. So you could start at 0.5 or you could start at 0.4.
Gotcha.
So, yeah, the quadratic would be simpler. So if we said 7.5 equals,
So that amount can't be zero at equilibrium, is that what you're saying?
oh, it could be.
But it can't be a negative number.
No, it could not be zero because of that value. It could be a lot of this, but there still has to be some of that. Otherwise, you divide by zero and that's infinity. So that's why I would pick something like 0.4. Minus 2 times 0.4. And this whole thing is squared. So that would be, bring this with me.
I just was like, just in general though, in the bigger picture, just that in a state of equilibrium, there's never going to be zero reactant.
Right,
There's always something. So
right,
it's not going to be ever a negative number in that column.
right. It could be vanishingly small.
Right.
Some reactions are like that. Yeah,
Probably there.
but
But that's why, just for logic's sake, like that 0.647
so this would be 0.2
doesn't work because it was a negative number.
squared equals 0.04. And then 7.5 times 0.04 is x. So let's see what that one is. That's equals 0.3. 0. So that would be x. And what you would do then was you would put 0.3 back in here for these and see what the value is. 0.3 divided by 1.0 minus 2 times 0.3, and then square that. So what is this? So that's 2 times 0.3 is 0.6, and 1 minus 0.6 is 0.4. So it's 0.3, oh, it's squared, excuse me, 0.4 squared. And then divide that into 0.3 is 5.3. Okay, so that's definitely greater, that's outside the 5%. Right, so now what we have to do is we take this value and we plug it back in here. And solve for x. So this is 0.4 squared. Let's see, 2.6, 0.4 squared is 0.16. So it's 7.5 times 0.16 is 1.2. So that's not even working. All right, iteration's not working. I don't know why. Okay, so rather than beat that horse, let's say, how do you know if you need to use in advance so you can use your time more efficiently? How do you know if you can assume x is so small that it's insignificant, or if you have to do the quadratic? That's your decision. You got to make a decision there. So let's see. What if 7.5 is our value? It's going to mean that since we've chosen x here, and 7.5 is large, greater than 1, we have to assume that x is also going to be large. So we can't say that x is small. If, however, the k is very small, like 10 to the minus 4, then we know that this value is going to be very small. And we can say, it's so small it doesn't matter. We can let it go and just square the value, and then go ahead and you're going to be safe. Does that make sense? It all has to do with the k. The k says whether you're going to be way over this way or way back this way. So I know what you're thinking. What if we made this x? Then this will be a half x. Well, a half x would still be too large to be insignificant. So if the k is large in this case, it's not in all cases, but in this case, since x is going to be very large, based on that, then we cannot ignore x. We have to do the quadratic. Now there are some situations that you're not going to have to deal with, where you may end up with a cubic equation or a coordinate equation. And there are solutions for that, but they're unwieldy, right? So we don't deal with those in this classroom. It's either quadratic or it's nothing, or it's easy. Okay. Let's see if I can find something else useful. How are we doing on time? 10 o'clock? Okay. 10, it shouldn't take too long. All but one of the reagents that you're going to need is prepared already. There's one they say you need to dilute.
This lab is the one that you said we aren't doing a formal lab report on.
Right.
And then we're just going to answer all the questions directly on this paper.
Yes.
And then, so are we writing this in our lab notebook?
As it'd be a good habit.
But for the final lab, where you check the lab notebook.
Oh, I'm not looking for it.
So this one's okay to not include in the
Yeah.
lab notebook? Okay.
It's just that if you try to put that information into the report as you go, if you make a mistake, then you still got to line it out and write in there in tiny words, and it just sometimes it's hard to follow if you make a mistake.
Especially when your handwriting is practically illegible at best.
So if you can put it in your lab notebook, at least to record the information, then fill out the lab report there.
I had a copy of that Word copy with the points and stuff on it, because where I printed it off, it don't have all that.
Oh, maybe I've got the wrong version in Blackboard, which I need to correct.
So that
I have another
copied it
copy.
into my notebook.
Yeah.
All of these lines make me sad.
It doesn't have the points on it.
No.
Yeah, that's good to know.
I copied it into my notebook last night, but I don't have it.
And that'll also give you a script if you mess up too much. You just rewrite it on the clean one.
Let me make myself a note.
So, while you're writing that note down, do you have an example of a question that uses this perplexing equation, Kp is equal to KCRT, power of delta n?
Which one is that?
Just a formula. I was wondering if there was a question that corresponds
Oh.
to it, because it looks horrifying.
Let's see. Where is it?
On the helpful information,
Yeah, I mean,
bottom right above the quadratic.
oh. Oh, yeah, let's see if we got one of those in here. That's where you, the interchangeability between the K using molarity versus, that should be K sub P. Is it K sub P in yours?
Yeah,
Okay.
KP is equal to KC.
Yeah.
RT delta N.
So if Kc is your K in terms of molarity, then you can use R temperature and the change in moles to find out what the K is in terms of partial pressures.
So I'm assuming this is with the system that uses gases.
Yes. Let's see. Do we have? I mean, I can make one up, but I'd like to use one that's already. Haven't found one yet.
I'm trying to go with, but I'm not exactly qualified one.
Okay, here's what we can do. We want to convert a K concentration to a Kp.
I hear it coming.
Yeah. There are two offices right through that wall. Maybe that's it. Let's see, where was I? Okay. Number 28. I think we did this one on the board already. Maybe we did.
Yeah, 26.
Oh, okay, so let's do 28 and then extend that to calculating the Kp. So 28 here, and then let's go back to 28 here. One mole of N2O4. Okay, so our equation is this one that we've seen before. Okay. And 1 mole of N2O4 is placed in a 1 liter container. So we're starting here with 1 molar. And it's allowed to reach equilibrium. So starting off there like that. At equilibrium, N2O4 is 37% dissociated. Okay, so the change is going to be 1 minus 0.37. 37% of 1 is 0.37, right? Okay, so that should be, actually, no.
No, the equilibrium.
0.37. Now equilibrium, you're right. 1 point minus 0.37 equals 0.63 volt. So that's our equilibrium position there. On this side, this is going to show up as 0.64.
74?
Huh?
0.74.
7.4, thank you. Yes. So here we have 0.74. Okay, so those are our concentrations, and now we can calculate K as equals 0.
7.4, why is it 0.74?
Because stoichiometry, 2 to 1.
Oh, that gets me every time. Dang.
So K is going to be this one squared divided by that one, 0.63. And 0.87. I did that right. Let me check myself. 0.74 squared and 0.63, 0.87. Okay, so that's our K in concentration units. And if we want to convert to partial pressure version, then what we need is, well, let's write the equation here first. Try to go from memory. It's going to be this one, and then times RT to the change in moles. Okay, so the change in moles is, what's the difference between this one and that one? So our K is 0.87. R is, I think R has to be,
Seems like the perfect gas.
yes, but there's, I'm debating whether it's 0.08206 or 8.314. I think it's 8.3145.
Why that one?
Because it has the energy term in it.
Couldn't you just use the 0.08206?
Well, let's see.
Because
This is molarity. And if we use the 0.08206 is liter atmospheres per mole K. I'm pretty sure it's 8.3145. Here we go. No, I'm wrong.
Either way, there are a couple of terms that I'm wondering how we can use those.
they get swallowed up by the K.
That's exactly right. 0.08206. Okay. So
Cookie Monster.
So it is this one.
I guess my brain thought it was that one because of the atmospheres, just because of the pressure being involved. So that's why I was choosing it.
Yes, thank you. That's exactly right. Okay, so what's the temperature? Are we given the temperature? Oh, we're not given the temperature. Okay, so since this one's not part of the problem, we're just going to have to assume a temperature. So we'll use standard temperature, which would be 0 degrees, or 273.
Standard temperature is freezing point of water. Huh?
Yeah, for gases.
Right.
Right. If there's nothing else involved with gases, then it's 0. So this would be times 273 K. And then what's delta N? Delta N is the change in the number of moles of gas. So we've gone from 1 to 2. So it's 2 minus 1 is the change. It's the final minus the initial. So that happens to be 1. So it's just that times that. Uh, 0.87, 0.08206, and 273. So now it's 19.5.
So what does that number mean exactly? I mean, we already calculated the K, so how's this KP relate to the initial K?
This K is in terms of concentration, molarity. This one is in terms of partial pressure. So we can take that value, and instead of using molarity up here, if we're given partial pressures for those values.
Oh.
Say this were 3 atmospheres. Then we could use that value to calculate what these concentrations are. Okay. Since we're not given units of measure, we have to know exactly where this thing came from, right? So partial pressures dictates that it's that pressure squared divided by this pressure. So this would be equal to NO2 squared divided by N2O4. Okay. That's what that represents. Okay. I learned something. Don't use 8.3145.
You're welcome.
Okay. Let's see. We didn't do any really. When we went through the PowerPoints, did I skip any ice tables? I get the feeling that I skipped this last one.
Which one are you talking
The one where the iron ion plus the thiocyanate yields iron thiocyanate.
You may have skipped that one. I didn't make any notes on it, so you may have skipped that one.
Yeah. So why don't we try that one?
The 3 trials, is that what you're talking about?
I'm sorry?
With the 3 trials?
Yeah, that would be, let's see, hold on a second.
Well, we did the,
Okay, yeah, I did skip the 3 trials.
we did do the first one.
Right, so we need to look at the,
We did it, and that's where you introduced the quadratic solution
right.
for the,
So what I skipped was the one where the trial 1, 2, and 3 are in green. Actually, the green is answers. The one above it. Middle of page 6 on the right.
right, that's the one.
That's the ones I skipped. Yeah.
Yeah.
Okay. So our equation is let's see, Fe3 plus and thiocyanate. Fe3 plus thiocyanate should be Fe thiocyanate 2 plus. They're all aqueous. Okay. So now, trial one. We're starting off with 9, 5, and 1. 9 molar, 5 molar, and 1 molar. Okay, and the K, where's the K? Can we calculate the K? Oh, there it is, 0.333. We did calculate that in an earlier problem. Okay, which is equal to divided by iron and cyanate. I think we're going to do this one today. That's one of our little exercises in there. We're not going to quantify it, of course. We're going to investigate in terms of the shot. Okay, so which direction is this going to go? Well, if we calculate Q, then we have 1, and then 9 and 5. Since there are no powers, we should be able to do that in our heads. Well, that's 1 over 45. That's definitely smaller than 0.33. Right? So if Q is smaller than 0.33, it's going that direction, right? Because this is too small, that's too large. If this is too small, it wants to go to that. It wants to go here. Q is less than K, goes to products. So that means equilibrium is going to say, we're going to end up with some of this. Well, let's see, what's the question? The amounts of each one at equilibrium. So this is going to add a certain amount of that. And since they're 1, 1, 1, we're going to lose some of this. There. Can you spell ice? So this is going to be 9 minus x. This will be 5 minus x. And this is going to be 1 plus x. Right. So our K is going to be equal to this one plus x, and this is going to be 9 minus x. This will be 5 minus x. Okay, so what's that going to do for us? Where's the K is 0.333. So it's going to produce a significant fraction of 1 is going to be x, because we're starting off with high values here. I doubt if we can figure that, saying that x is really very small. We're going to have to use quadratic.
So we're going to have to FOIL it out.
Yeah, we're going to have to factor it out. So, what happens on the bottom? Well, 9 times 5 is 45. Oops. And then minus x times minus x is x squared. And then 5 times minus x is minus 5, and minus 9 is minus 14. X. And then a third of each one of these. Because 0.333 times those. So 45 is 14.99 minus 14 minus 4.66 x, and then 0.333 x squared. And that's equal to 1 plus x. So we have to bring this 1 over here, which makes this 13.99. And then bring the x over, which makes it a minus, which makes it a minus 5.66x, 0.333x squared equals 0. This is our A term, this is our B term, this is our C term. Did I lose anybody? Or do I need to move this thing? Yeah, you can still see it. So now, x equals minus b minus a minus 566 plus or minus square root of b squared, which is minus 5.66 squared, minus 4 times a, which is 0.333, and then c, which is 13.99. Oops. Yeah, 13.99. See if I got all my signs correct. That one squared 4 times.
Is the quadratic thing on the useful information page?
Is it? Should be.
I'm asking.
Yes.
It is.
Yeah, it should be there.
Where at? Oh, right there, okay.
And then A is 0.333. There we go. So, what can X be? All right, so we have, that's a 5.66, and then we have this term resolves to what? Square it, and then 4, 3, 99. Minus. So this term right in here is 13.4. Square root of that is 3.66. Okay. So this is a positive 566. And we're going to add first. And then divide by 0.667, because it's 2 times that. So the first possibility is 13.97. Or, that can't be, because 9 minus x is a negative number. So it has to be the second one. So this would be 566 minus 366, right? Then divided by 0.667 is 2.999, or about 3. So that makes this one 6, makes this one 2. It makes this one 4. 6, 2, and 4.
So those are the
6, 2, and 4.
So those are the concentrations of equilibrium.
Yes. Yes. Right. You have to plug that X in here because X is not the answer. X gets to the answer once you apply it to the equilibrium expressions. Okay. So I just rounded off to 3 because if we rounded off to 2 places, it would be 3.00. There you go.
I don't feel like we need to go through trial number 2 and 3. Do you guys like?
I don't either.
I feel like that was sufficient.
I at least know how to use the quadratic equation for these. And I think I have an understanding of when to use it. It's when you're finding equilibrium concentrations.
Yes, and
Partial pressures.
right, and the value here tells you how significant is that X in the equilibrium expression. That one tells me that it's too large to ignore. Right, because this is going to be a reasonably large value. I mean, it's not super large, but it's large enough where you cannot ignore it.
Like, can we use that if it's a small?
If this value is 10 to the minus 4th, something like that, then yeah, that X will be so small that you can ignore it in, where is it? Here. In that case, the X will be so small that you could say that's 0, so it'd be 9 times 5 is 45 divided into 1 plus X. Then you could just solve for the X. And the way to prove that it's right is to plug that X back into this expression and see, is it within 5% of that value? Okay. All right. So we can stop this in the meeting.